So we're going to look at advanced modeling with systems, and we're going to use some real-world situations, although let's be honest, this isn't going to be very much a real world when we're talking about the tortoise and the hare, and as you're going to see, a rat. But it is an example I found some time ago, and it works really well for our situation. Scenario number 1. The tortoise and the hare finally have their long-awaited rematch. We're going to give the tortoise a 1,000-foot lead, but the tortoise is going to run at 9 inches per second. The hare begins at the starting line and runs at a rate of 6 feet per second. There will also be a rat in this race. The rat will start 1,200 feet ahead of the hare, but is going to run back towards the starting line at a rate of 2 feet per second. The race will be a quarter mile long. The first question we're going to ask is, could you please set up the linear functions using function notation for the tortoise t of x? So we're going to need a tortoise equation. Which we'll call t of x. We're going to need a hare equation, which is going to be h of x. We're going to need a rat equation, which we're going to call r of x. And as goofy as it sounds, we're asking you to come up with a finish line equation which we're going to call f of x. All 4 of these I would like to use slope-intercept form. Okay, I'd like to use slope-intercept form to write them. And the reason I think slope-intercept form is the best is that m, which is slope, is also known as your average rate of change. So if we could find things that might use the word per, we'll need a variable, independent variable of x. We'll need a plus b, and this can be our initial value because normally it takes on the role of y-intercept, but that's what a y-intercept is. It's essentially a starting point. What we have to watch out for, and I'm going to highlight this, is that we're not always talking the same unit. Here we got 9 inches per second. But over here, I was talking about 6 feet per second. I was talking about 2 feet per second. I've got a quarter mile long. And I also am talking about 1,000 feet, 1,200 feet, and all that. We really need to standardize our unit so that we're consistent. And to me, the easiest thing to do to make it consistent is let's convert all these to feet. So this may be 9 inches, but I think it would be better to call it 0.75 feet per second. And since a quarter mile long, a fourth of a mile, would be a fourth of 5,280 feet, that'd be better to call this 1,320 feet. But everything else seems like we'll have no issues. So we're going to put everything in terms of feet for our work. Let's start with the tortoise. Instead of saying 9 inches per second, which would be his rate of change, or it's her, I shouldn't be sexist. All right? We'll say 0.75. I've already said that x is going to be the variable, so x is going to have to be the number of seconds. So 0.75x. Now, that's the rate the tortoise is changing, but now I have to know where he or she started. And in this particular case, the 1,000 foot, this would be my initial starting spot. So I'm going to add 1,000 to the torus's distance. That's how I would set up this particular equation. Per is a good word for finding your rate of change. I'm going to do the same thing for the hair. The hair, right here, says traveling 6 feet per second. So I'm going to go 6, multiply it by the number of seconds. I'm not going to need to put down a starting value if the hair's got no head start. So technically, it could be 6x plus 0, but let's be clear here. I very rarely would put the plus 0. But what about the rat? I'm actually going to start with his or hers starting spot, which in this case was right here, the 1,200 feet. So the rat is farther along than everybody else. But the reason I did that is you'll notice that it says that he's running back towards the starting line, which means he's getting closer and closer. He's not adding on to his distance, he's decreasing his distance. So that's why he's going to be a negative 2x. Finally, the finish line. As goofy as it sounds, we can write an equation for this one. Now, where it starts and where it ends, this always stays the same. It will always be 1,320 feet from the starting line. I did put a plus there, but let's be honest, it's never changing, so it has no change in slope, and so therefore I probably don't even need to put the plus here. It probably should be in yellow, meaning it always is 1,320. And that leads to my question. Which of the functions is or are constants? And the only one that never changes is f of x. It's the only one that never changes. Now let's go ahead and review some vocabulary terms from the past. Direct variation. A direct variation is essentially where you have a constant rate of change, but you did start at 0, 0. The only racing animal that actually starts at the starting line and proceeds to move at a rate consistently throughout would be the hare. So the hare's function would be our example of a direct variation. Which ones have positive slope? The ones that have positive slope would be the ones where the rate of change is adding distance from the starting line. As you can see, the tortoise is moving forward. The hare is moving forward. The rat, however, is moving back towards the starting line and therefore would have negative slope r of x. Identify the independent variable and its meaning. The independent variable is what you use to plug into the equation. This is the independent variable right here. It's what you plug in. It's right there. So as I stated, it's x. And the whole idea about this particular situation is that x represents the number of seconds into the race. I don't know if that's the best way of saying it, but that's what I've used in the past. Now it's saying, please label on the graph on its appropriate axis. You're saying, what graph? That's why I need you to turn to 2 pages from now and look to page 3. And I need you to label this graph that was designed in GeoGebra and put that down here. This is going to be x. And you don't actually have to write x. And let me zoom in a little bit on this. But you should definitely be saying number of seconds. Or just say seconds. Let's go back to the first page. Identify the dependent variable or variables and their meanings, because dependent variables are all the outcomes, essentially. And we know that we need one for the t. So t of x would be your dependent variable, but then so would h of x. Technically, so would r of x. And I'll include f of x, but honestly, I'm not really too worried about it. But it is part of it. It's one of the 4 equations, so I probably should include it. But the 3 that I'm really interested in is t represents the tortoise's position in the race. H of x is going to be the hare's position in the race. I'm not going to keep writing in the race. I'll just do the little quotes. And R of x is the rat's position in the race. If you want to include f of x, which I would understand because we did write it down, technically it's the finishing line's position. But the finishing line's position is a constant, so it really isn't going to be drastically unique. All of these, you should know, are going to be feet specifically from the starting line. We have to understand where we are. And so it's asking us to label this on the graph of its appropriate axis. So I'm going to hop back over here to the 3rd page. And this is why I said it was probably not necessary to write x equals, because this is called the x-axis. Over here, this is the t of x-axis, the f of x-axis, the r of x-axis, the h of x-axis. So really when it comes down to it, the unit is in feet. If you want to say feet from the starting line, that's never a bad thing to include. So what we're going to do now, as I said, I wanted to kind of explain to you how to get these graphs on the computer system so that you can start learning how to copy, paste them into your document, and then use them, is let's introduce you to GeoGebra. G-E-O-G-E-B-R-A. GeoGebra. It should be one of your apps on your Chromebook. What we're going to do is we're going to graph each of these equations. I left it as x because GeoGebra doesn't know how to use other variables besides x and y unless under different circumstances. It does know how to use t, but that's not what we're going to deal with. So it's pretty straightforward. And here's the nice thing. It does accept algebra function notation. It does accept that. So if you come up here to the plus, and we want to type in the tortoise's formula, you can actually go t of x. You'll notice as you start typing it in, you might start to see things popping up. Like if I type in 0.75, it thinks right now it's a constant. And so therefore it's trying to graph it at literally 0.75 always. But the moment I multiply it by x, then we now have a direct variation. The problem is I want this to be at least 1,000. And 1,000 is way, way off the screen. But feel free to go ahead and enter for this. Now, would you like to see your equation? Here's the problem. This is supposed to be at 1,000 for its starting value. If you look at your graph, we're at 9. There's a couple ways to getting to this. I will show you one way, then I'll show you another way that I think you might like, although if you're using a Chromebook, it's not always easy to work with. I have the advantage of having a mouse. If you right-click anywhere in the graph, you should be able to find something called graphics, okay? And you can see all these different options, but honestly, it's probably just easiest to go to the properties, which in this case is called graphics again. And up will pop a window that will give you your window settings. I'm going to ask you for your x, which x is right now our seconds, realize we're not going to go into negative seconds. I'm going to ask you to use a few negative seconds, but only so that we can have the numbers off to the side a little bit. So why don't you go ahead, and by the way, I do realize this is going to be hard for some of you to see, so what I'm going to do is, if you want to click over here to the menu, you can change your settings so that I can use a larger font. So I'm going to go back here, I'm going to click on settings, graphics, and let's start our X min at -10. So let's pretend that we could go 10 seconds behind. I don't know why I didn't accept it, but let's try it again. -10 for the X min. Now, I don't know how long this race is going to be, so I'm going to ask you to go 350 seconds. I'm not sure why this is not accepting. I keep hitting it, but it doesn't. There we go. We're not going behind the starting line. The rat could eventually get past that. I mean, technically it doesn't stop. But I do like to have a little bit of negative so I can see the numbers on the bottom without conflicting. So let's just say we'll go about a -100. And we need to get past this finish line. The finish line is at least 1,320 feet. Let's go 1,500. Oh, look, there's your graph. Now, if you do not have this equation, you can always go back and edit this equation. You can click here, and you can type and make corrections. Now, let's just say you didn't want all this extra room, or you wanted to zoom in or zoom out. So watch carefully. If you have a mouse, you would be using the left click. But if you move your cursor on top of an axis, hold the shift key down, notice that my cursor changes. Hold it down, and you can actually drag this up and down to make whatever adjustments you need to do. If you think you have too much time, you don't think this race is going to last 350 seconds, you can come down here to the x-axis, click on it, drag it out, spread it out more, have less time. If you think I didn't go far enough for the race, drag it back. Please note, I am not asking you to know that this has to be the numbers. It just has to be a decent looking graph. So what we're going to do is we're going to graph all 4 of them, and then we're going to take a look to see where we're at. So let's go ahead now and put in the hair, which I will type in as h of x. The hair travels at 6 feet per second. I don't need to type in a 0, +0, because it's not necessary. And I'll hit enter, and there's the second graph. R of x will be -2x plus 1,200. There's the rat. That's how the rat is traveling. Eventually, the rat looks like it should cross 0, go back to the starting line, but it may take a long time to actually get there. I want to make sure I have enough time that I can see both the hare and the tortoise crossing the finish line, which is why I'm going to put in the finishing line. So I'm actually going to see when that occurs. So here's where the 1320 goes. Hey, look, here's the hare. At this time, it's going to cross the finish line. Oh, look, the tortoise is going to cross the hare, but I didn't go far enough over. It's going to be way out at this time. So let's be honest, the hare is going to win this race. We're going to go back to the first page, which is right here. And one of the questions I ask very simply is, hey, tell me what's happening at different times in this race. Why am I asking you to do this? Because I want you to practice your function notation. That's it. So if I ask you to demonstrate with function notation how to make a prediction, this would be a good way of doing it. For instance, where is the tortoise going to be at the 45-second mark? It's pretty easy. You want x to be 45. So literally say t of 45. Function notation basically says, all right, you just told me x is 45, so wherever I see an x, I'll fill in 45. Now that number will get 45, will get multiplied by 0.75. I'll then have to add 1,000, and estimating this, or I have is, or was it exact? I don't remember, but it ended up being 1,033.8. I think it was rounded to a decimal place, 8 feet. Okay. At the 45-second mark of the race, the hare would be 6 times 45. This works out to be 270. And R45, it works out to be 2 times 45 plus 12, negative 2 times 45 plus 1,200. And if you type that in, you'll get 1,110 feet. Again, this is all from the starting line. So one of the questions I simply want to know is, who's winning the race as of right now? And you can see that the rat is farthest away from the finishing line. Tortoise is not that far behind, but at the 45-second mark, the hare is closest to the starting line, which means the hare is coming in third place as of right now. I ask you to do one more function notation, but the reason I did this one is you'll notice it says the 2-minute mark. What's the issue? It's not in seconds. So 2 minutes equals 120 seconds. Therefore, when I do this all over again, I should be using 120. So if I do this, and by the way, think of this when you're doing your project, and I ask you, please show me the work using function notation. This is exactly what I'm talking about. And you'll come up with 1,090 feet. If I do h of 120, which is 6 times 120, you'll come up with 720 feet. And if you do r of 120 plus 1,200, you'll come up with 960 feet. And so now at the 122nd mark, we're going to have the tortoise now being farthest from the finishing line. The rat is now moved into second place. The hare is still behind because it is still closest to the finish line. So what I'm doing now is I've pulled up a version of the project, or in this case a GeoGebra, of the same activity. But what I did is I added locations for the rabbit, the hare, and the tortoise. Here's going to be the hare down here, tortoise here, rabbit here. The finish line is this line right here. So when you cross the finish line, you win. Let's move to 45 seconds. And you can see off to the side exactly how they're being positioned if you actually saw a race. So at 45 seconds, these are the numbers that you came up with on this page a few moments ago. Let me pull that page up. 1,033.8 feet, 270 feet, and 1,110 feet are represented right here. If I move to 120 seconds, you can see how the hare is moving up fast. The rat has now moved into second place. And now we have the same answers as 1090, 720, and 960.